Hi, this video is to explain what a pycnometer is, how they're calibrated, and what some of the different advantages and different disadvantages of different pycnometer designs are. So a pycnometer is a rigid container that has an interior volume that's very precisely defined, so that every time that it is filled up, we can be very certain that the volume contained inside is exactly the same. So a pycnometer has to be made out of a rigid material. Around the lab, we wouldn't use a container that had any degree of flex in it or was soft, or we wouldn't use one that had a lid that had a cork or a rubber stopper, because those don't go into the same, contain the same volume all the time. So common pieces of equipment that would be used as a pycnometer, it might be something like this. This is designed to be a volumetric flask. Usually this would be filled up to that line in order to know that exactly 100 milliliters had been there. But it works well as a pycnometer because it's fairly rigid. It's hard to compress it and change its interior volume. And it also has a feature that a lot of pycnometers do have, which is that it has a tapered stopper. When we calibrate a pycnometer, we fill it up with water and we calculate its interior volume using the density of water. So it's important that when we have it immersed in the water, when we put the lid on, that the lid goes down to exactly the same depth all the time. And with a tapered lid, that's possible because if it's fully immersed in water, as the cap goes in, water can come out. It can be squeezed out along the taper like this. So tapered joints are higher quality and they always go to the same depth if you press them with about the same amount of force. This is a glass volumetric flask that could be used as a pycnometer. This would in principle be a better pycnometer because glass is more rigid than the plastic. It is smaller though, so when we measure the mass of this, we will get more significant figures. So one advantage of this is that it gets more significant figures when we measure its mass, and a different advantage that this has is that it is truly more rigid and its interior volume does not vary as much due to flexing or pressure. A third type of pycnometer is based upon a very different kind of a design. This is a pycnometer which started off in life as a centrifuge tube. And as a centrifuge tube, if we just tried to immerse it in water and put the cap down tight, if we looked closely, we would see the top cap here would be bubbled with a different amount on different occasions. In other words, different amount of water would get trapped in there. But in order to overcome that, this can be made into a very good pycnometer by putting a small pinhole in the cap here. That way, as the pycnometer is immersed underneath the water, as we tighten up the cap and the volume is squeezed down here, it will always close to the same exact volume. The top will not flex or up or down in response to that. So this works very well as a pycnometer as long as it has a pinhole in the top. One other disadvantage, though, once you have filled this with water when you're calibrating it, or if you're working with it with a solution, you're trying to determine the density, you have to be careful not to squeeze it because you don't want to push water out and suck air back in. Now, the first step in calibrating a pycnometer is to determine the mass that it has when it's empty and dry. So for each of these three pycnometers, I'm going to measure their empty dry masses on my scale. I'll turn the scale on. I'll wait for it to boot up. And it reads 0 now. If it doesn't read 0, you should tear it. And then put the first pycnometer on there. 24.23 grams. I'll take my second pycnometer. 13.24 grams. And the last one, 27.63. The next stage in calibrating a pycnometer is to prepare a water bath of known temperature. We usually prepare this bath at a temperature that matches the room temperature so that it doesn't change throughout the experiment. So I took the hot and cold water at the faucets and I adjusted until they were filling up the pot with water that was just at the same temperature as the room. First, you take the pycnometer and you want to fully immerse it. Okay. Then shake it out, tap it against the walls, make sure there are no air bubbles, and then rub the cap to make sure there are no air bubbles stuck onto the surface of the stopper. I'm doing there. Then, without taking it out from under the surface of the water, insert the stopper gently. Move it back and forth to make sure you reach the full depth that it wants to be inserted, and you'll feel, with a glass stopper, you'll feel the glass grip. Okay. You take it out, and you want to invert it to make sure that you don't see any air bubbles in it. All right, there are no air bubbles coming up and down. So we can put this on the side and get ready to dry it out next. Then I'll take my next pycnometer, and I'll fully immerse it again. And I'll do the same thing. I'm going to tap to make sure no air bubbles are stuck on the walls. Then I'm going to immerse the stopper, rub the stopper to make sure it doesn't have air bubbles on it. And then gently and firmly insert the stopper to its full depth. Again, I'll take it out and I'll invert it to make sure I don't see any air bubbles. Okay, I'm going to put this on the side and get ready to dry that off also. And finally, I'll take my last pycnometer and I'll do the same thing. I'm going to fully immerse it, make sure there are no air bubbles. I'm going to rub my fingers in by the threads here to make sure there are no air bubbles caught there. And I'm going to gently tighten the cap as far as it will go. And when I do that, if I hold my finger right here by the pinhole, I can feel water be pushed out as the cap becomes tightened. With this type of pycnometer, you have to be especially careful that as you take it out, that you're very gentle with it. You don't want to squeeze it, because if you squeeze it, water will come squirting out of the pinhole here and air will get sucked back in. So you just want to take it and gently put your finger over the pinhole and invert it to make sure there are no air bubbles. Doesn't appear to me that there are. And then we can put this on the side and get ready to weigh it as soon as we get a rag. Now, using a clean, dry rag, we want to thoroughly dry each of the pycnometers, taking a lot of care to not disturb the caps. We don't want the caps to move and for air to be allowed to get in. And make sure, using a soft rag, that we get into all of the cracks and crevices, including, for instance, in this pycnometer, towards the top here, while holding my finger to keep the stopper in, I'm going to work into the cracks. Okay. And I'll dry this one off with similar care. I'm going to be careful in this with this pycnometer to not squeeze it. I don't want any water to come oozing out of the pinhole that's in the top here. I'm going to very gently do it. And as I twist it, I make sure that I twist in the direction it would tighten, not loosen the cap. All right, the cap is on very tight now, so it's not going to move and get any tighter. But I want to make sure that as I get into the cracks and crevices here, that I do not loosen the cap. Okay, and to confirm that I've done a good job, you shouldn't be afraid to invert it and make sure that there are no air bubbles that have been allowed in. Okay, now this has been thoroughly dried. Okay, and finally to our third glass pycnometer. Okay, again, I'm going to take care to make sure I don't move that penny head stopper at all. All right, but I'm also going to use the edge of the rag to get into the cracks and crevices here. All right, and absolutely dry this off. Now, the next step in calibrating a pycnometer is to measure the mass with it filled with water at that known temperature. So I'm going to turn my scale on and allow it to boot up. And once it reads 0, I'll put my first pycnometer filled with water on there. 122.15 grams. So I record that, and I'll put my second pycnometer on here. 69.73 grams. And finally, I put my third pycnometer, 55.465 grams. The next step is to use the mass of the pycnometer filled with water and the mass that it had empty in order to calculate how much water is captured inside of the pycnometer. So I've done that calculation for all 3 of the pycnometers here. They all were filled up in the same water bath, which was at 27.3 degrees Celsius. One of the reasons that a pycnometer is such an excellent device to measure the volume is that we determine the volume of the pycnometer based upon a mass measurement. And in most laboratories, the scale is the device that offers the most significant figures that can make the best measurements. So the way that we're going to figure out the volume inside the pycnometer is we're going to use the density equation, but we're going to rearrange it for volume. We want to know the volume of water that is inside each of one of these pycnometers. And we're going to do it by taking the mass that we just calculated and dividing it by the density, which we can look up. It's an accepted quantity, the density of water at any given temperature. So the next step is to look up the density at the temperature of a water bath, the temperature that we filled these containers up at. So that was 27.3 degrees. And if we read this table properly, the density of water at that temperature we have to 7 significant figures, which is shown here. So for our first pycnometer, the plastic 100 milliliter volumetric flask, the mass was 97.92 grams. And we're going to use that density that we just looked up in order to calculate the volume of water and the interior volume of that pycnometer. So the volume of this calculates to 98.27 milliliters. That's an important quantity that we should write on this flask that we'll always use every time we use this flask in the future. We should also write its empty mass. That's used often in pycnometer calculations. So that's critical information. We have that recorded on the pycnometer, so we can always use it going forward in the future whenever we use it with other solutions in this pycnometer. If we repeat the same type of calculation for this pycnometer, we find out the volume is 56.69 milliliters. So we should record that along with the mass of the empty pycnometer on here with a permanent magic marker. So that's what I've done here. So that when I use this pycnometer in the future, I know its mass and its volume. And finally, I'll take the mass of water that I calculated to be in this pycnometer and divide it by the density at that temperature to calculate the volume in that pycnometer. And that calculates the 27.92 milliliters that I'm going to also record on this pycnometer.